Alright, let's talk about the last section in the chapter, relative motion of two particles, and this is using translating axes. So, this might not make the most sense at first. I'm going to do my best. I'm going to go over how the book explains this first, and then I'm going to use a couple examples to try to reiterate the point, because you see this in everyday life without knowing it. If we have some fixed observer right here, and someone that's traveling in some traveling reference frame that will give primes. So it's got a x prime, y prime, and z prime. And they're both observing some particle B moving along some path. So it could be moving along with some velocity or acceleration. And let's call this an origin. Let's call this A. And we called that B already. Okay, from the origin we can identify where B is by drawing a vector to it. We'll say that is the position vector B. From the translating observer we can also make a position vector, and we can also draw a position vector from the origin to the translating observer. We'll call this one RA. And if we do the vector addition, we can say RB is equal to RA. Plus this thing right here, R of B with respect to A. You'll also see this in R of B with respect to A is equal to the difference between the two. And this one sometimes makes more sense, but I'll explain why we use this one often. This one makes sense to me when we're talking about the relative velocity or position of something B with respect to A. It is literally by definition the position vector B minus the position vector A. And those could be velocities, anything that's a vector. The reason we use this is not so much for this chapter even, or the following few chapters. The reason is we're going to start looking at, what if we have a rigid body, we can say it has some point A and some point B. Well, we can say that the motion of A, or the position of A from some origin, right? Here's some origin. If we take that and add the position of B with respect to A, we will get our position of B. And we're going to use that because if we take derivatives of this, we will get that the velocity of B is equal to the velocity of A plus the velocity of B with respect to A, and the acceleration of B is equal to the acceleration of A plus the acceleration of B with respect to A. Okay, now if we start looking at general planar motion, that'll be chapter 16, when we'll have rigid bodies, and they're going to be doing two things. They will be translating and rotating. Right now we're dealing with point masses, so we have no rotation to deal with, just translation. This specific section would deal with the motion, and say you have one plane flying this way with a velocity of 100 miles per hour, and you have another plane flying this way at 200 miles per hour. Well, then if this is the velocity of A and this is the velocity of B, you can say the velocity of B with respect to A is equal to 200 minus minus 200 minus a positive 100. So with respect to each other, they are going 300 miles or miles per hour past each other. Same thing if maybe you were driving 60 on a freeway and someone passes you doing 65. That difference right here, this little vector, is your velocity of b with respect to a, and you can say the velocity of b with respect to a is equal to, it'd be the 65 minus 60, or 5 miles per hour. Okay, so that's mainly what they're trying to hit on in this chapter, but I really want to pound in the point that we're moving into general planar motion and rigid bodies in chapter 16. And what we're dealing with is, imagine another rigid body or a member or beam at some AB, and at some later time it moves over in space from the origin, but it's also rotated. To analyze this motion, we're going to need to analyze what happens with A, the translational motion, and then look at the rotational motion that happens to cause B to move over here. So the velocity of B would be equal to whatever the translational velocity of A is, plus the velocity of B with respect to A. And this would be our rotation. We don't know how to deal with it yet, but I just want to really emphasize where we're going to see these equations the most in our future. We'll also have the acceleration of B would be equal to the acceleration of A. So if it's accelerating in that direction and then has some angular acceleration, we can get acceleration terms for those, and it would look just like that. So this is in our future. I don't think you're going to see much on section 1210 on any problems really until we get to chapter 16. We start rotating stuff. But it's good to know, right? If all we're talking about is if you're walking 5 miles per hour, someone else is walking 6 miles per hour, their relative velocity compared to you is 1 mile per hour. If they're accelerating, we would handle it the same way. So don't make too much of it. Feel free to go over the examples in the book. I don't think I ask you any homework problems regarding this, but we will absolutely be using it in chapter 16. Every problem, pretty much.